Good day. This is Raymond Monroe. We're doing a casting webinar series for purchasers and customers and foundry people, really beginning this session on a series of webinars that will give you an overview of the casting process all the way back to design. And we're going to start at the end of the process with a casting inspection where we confirm that we've met all of the requirements that the customer or purchaser intended for us to meet. We're making custom products, and so every product we make, virtually in 1 to 100 pieces, they're all individually specified with a unique set of requirements. And so we need to do a final inspection and certification to ensure that we've met all of the requirements that the customer has imposed. And so when we look at it, we're going to go through the process backwards. And so we're starting with basically non-destructive testing, or actually inspection, including dimensions of the final casting. This is when we're ready to certify that we've met all the requirements. We do that to ensure that we've met your needs. One of the things that we have to do, if you've ordered the material to ASTM, it is fundamental that we have to do a visual inspection. If you order, as it says in this first section, to ASTM standards, they all call out A703 or A781 as general technical delivery requirements. And the language in paragraph A for 781 on quality says that the surface of the casting shall be free of adhering sand, scale, cracks, and hot tears as determined by visual examination. So this imposes on the steel foundry, when you just order a material to any of the ASTM specifications as a cast grade, that they have to do a visual inspection to make sure that it's free from adhering sand, scale, cracks, and hot tears. The challenge is, of course, that none of these terms are actually defined in the standard, and there's no standard test methodology. But it is absolutely correct that I can't send you something that we would just, in our ordinary language, consider a casting with a crack in it. So when my customers are concerned that I might ship a casting that has a crack in it, I'm unable to do that because I would be violating the purchase agreement. Beyond that, and you can see these 3 dots, that paragraph goes on and says if you're really interested, you could quote ASTM E186 to further specify the surface condition. And there's really 3 different common surface comparators or surface standards that you can look to specify the surface finish. The oldest one, the one that's most commonly cited, and the one that may be, in fact, the least useful, is the MSS SP55. This is an example of type 12 surface roughness, and this one is considered acceptable. This one's unacceptable. So you can see that if we're looking at the same casting and I am the foundry, I think that the casting looks like this. You as the customer thinks the casting looks like this. And so we really have a difficult time agreeing on what that means. In fact, most of the non-destructive standards are really a handshake between the foundry that's producing and the customer that's buying it, because none of these standards are quantitative where you can get a measurement as a refereed standard. MSS P55 is the most commonly referred to one, and it's a series of pictures you get from the Valve Manufacturers Association. Strata, or now CTI in the UK, developed a series of 4x6 kind of plastic plates with different surface finishes, and you can specify in ASTM E186, even MSS SP55, the newest version, refers to these same strata plates. So these are the most commonly used. They're really expensive, and they really don't resolve the problem of subjectivity. You know, if I say I want MSS P55, does that mean that I have to be this good or better to be acceptable? Or do I have to be this bad or worse to be unacceptable? And so there's some real openness, and the same thing's true with the strata roughness plates. That do I need to be smoother than this, or is this acceptable still? And then, of course, in investment casting for these finer surfaces, you have the GAR C9 micro finish. That's one that's commonly used to look at surface finish. These were intended to be RMS, but we've done measurements now, and these numbers aren't really very meaningful in terms of characterizing those surfaces. And because of the uncertainty here, we're actually working with Iowa State University and Frank Peters to try and come up with a white light or a laser scan method of quantifying the surface finish and quantifying those irregularities like pores or scabs, so that we could have a numerical standard, because without a clear referee standard, I don't know how to comply. And when commercial conditions change, it's not clear if the standard remains the same. If I've got a lot of inventory in the system and the market has cratered, then my customer, who would accept a really rough surface when we were operating at capacity and I couldn't ship him enough product, suddenly becomes really particular on the surface finish. And so it'd be really helpful both to the foundry and to the customer to have a standard method of measuring. It would also allow us to clearly communicate what's required and to assess whether or not it might have an effect on performance. But in general, there's no effect of performance on surface roughness, because the surface roughness is not as coarse as the microstructure. So in general, the specification of surface roughness has to do with the appearance of the casting to the customer and to his customer. And so that's the general reason that we do all of the really additional finishing we do for visual inspection. We found this out pretty early because we were trying to understand why it's difficult to manage the finishing area where we grind and try to complete the surface finish requirement. And when we did that, we found very quickly that one of the biggest challenges is the visual inspection process is not repeatable or reproducible. So here's the same casting evaluated twice by the same inspector by two different inspectors. And you can see how variable their results are. This is a fundamental challenge, not just in visual inspection. It turns out that everything except ultrasonics is a visual evaluation of a picture, whether it's magnetic particle inspection, liquid penetrant inspection, or even radiographic inspection. I'm really doing an ink blot comparison with a picture. And so that makes it really challenging. So while our as is that the specifications work or seem to work in terms of managing the quality aspect, they're really not directly related to performance. And so if you look, the advantage of visual inspection is it's relatively fast and low in cost, but it really doesn't give me any permanent record and doesn't really allow you to get at very good reproducibility. So we actually did a lot of work on the inspector. We found that even within our customers as well as the foundries, we might not even make sure the guy can see that's the inspector, do a visual acuity. So we actually developed a test to see whether or not somebody had the temperament to do inspection as well. So as I mentioned, the unaided eye for visual inspection of the surface, but we also are visually interpreting penetrant inspection, magnetic particle, and radiography. We have two different ways for non-destructive evaluation, and I grew up with mechanical engineers who said, since I'm not breaking the part, it's an evaluation. The industry seems to have adopted pretty uniformly globally non-destructive testing, NDT, is the right way to talk about this. We look at the surface and we do that with visual inspection. You could do it with eddy current, which we don't use in castings. You can use liquid penetrant or penetrant testing, magnetic particle testing, or magnetic particle MT. And typically for most steels, they're alloyed steels that can be magnetized. And so the most common surface inspection is magnetic particle testing. In internal inspection, we typically have done radiography, especially on first article, but for critical components and thick sections, we'll use ultrasonic testing. Castings with indications are not defective because I haven't transferred the ownership yet. I am trying to meet all of your quality requirements. And so when I find indications, if they're unacceptable, then I'll continue to work on the part until it meets all of your requirements. One of the things you should be aware of, though, is that these NDT standards were not developed or based on the performance of the part. They have no direct indication of how well the part will fare in service or what kind of load it will keep. It's really workmanship. So when you go to these standards and look at the acceptance criteria, the middle acceptance criteria is the common commercial expectation. And if you need something more than that, you can tighten it. Or if you're willing to take less than that, you can go below that. So for example, in radiography, level 3 is the common indication, the common recommendation that we give for radiography for a structural steel casting. Here is a list of the specification. I'm not going to go through them, but this is just, you can get this on our Wikipedia or on our website. You can get this set of graphs and you'll be able to look at these specifications. One of the challenges we face is everybody talks as though once I find something in non-destructive testing, that's a defect. It's not a defect until I try and transfer ownership to you. And so what I'm really doing is trying to meet your quality standard. And I find conditions, whether it's a lack of heat treatment, mechanical properties, a lack of dimensional conformance, or something that doesn't meet your non-destructive testing, I continue to work until I meet all of your requirements, and that's why I do this final inspection. One of the challenges we face is that our non-destructive standards really are back from the slide ruler era. And because of that, commonly in the past, large industrial companies would test to failure the parts, and they would test parts that didn't quite meet the standard to make sure that they complied. One of the things I recommend now is if you want a good briefing on the tight NDT standards for safety critical parts, you can go to the ASME boiler and pressure vessel code. And so that's what I would recommend if you have a safety critical or a life critical part, is that you look at the boiler code, because it sets non-destructive testing standards for all kinds of nuclear power plants and other things. You also want to work with a foundry and look at what the value added is. Magnetic particle examination, MT. This is the most common method, and it's really good at finding cracks. Typically, we would suggest that you don't want to accept anything over 1/4 of an inch as the first place to start. But of course, much larger castings, you might want a larger indication. And if you're looking at investment cast jewelry, 1/4 inch is too big. But for just ordinary common structural steel castings, about 1/4 of an inch. Magnetic particle can see below the surface, but you don't have any confidence or guarantee that it will. And MT, you magnetize the part, and if there's a crack, then you get the powder lining up, just like when you put a magnet under a piece of paper and sprinkled iron filings when you were in high school or junior high school. One of the challenges is people want to make really tight standards. So we have a nuclear power code uses about 1/4 of an inch standard. And there you've got about a 50% probability of detection, and you don't get much better beyond that. So that's actually a commercially usable standard. But people will use half of that standard, 1/8 of an inch, and you can see you only got about a 25% probability of detecting those. So you really aren't improving the quality expectation of the part, but you are spending a lot more money polishing out little pits. This is the repeatability, and you can see our repeatability, you get about that 15% probability of detection. We actually looked at the indications, because the challenge is everyone thinks that these linear indications are somehow cracks. But if you look, we drilled holes, and the holes, round holes, have the same effect on performance that the indication does in terms of strength. And the same thing is true in terms of the ductility. The ductility falls off not because the material is not ductile anymore, it's because we've localized the fracture by putting a notch in the bar when you have porosity or when you have a hole. These are huge holes, by the way. So this 25 1/4 of an inch is in a 505 specimen drilled halfway through the specimen. So you don't lose very much yield strength at all with these indications. We're actually trying to improve this by standardizing the magnetic particle. So we have a large program trying to get it better NDT. So if you're interested in this, we're trying to get a quantitative NDT and get much better at this with a big program we have called the Digital Innovative Design Program. And if you're interested in that, you can drop me an email and we can try and get you involved in that program. We also use liquid penetrant mainly for non-magnetic alloys like stainless steels. it's more sensitive, and so it finds a lot of things that aren't very important but causes us to polish the surface more frequently. So we prefer magnetic particle, which seems to give a better indication of the engineering content, but we use liquid penetrant when the material won't be magnetized. And in penetrant testing, you put in a penetrant, you wipe it off, you put a developer in it, pulls the penetrant back out, it glows in a black light, and that allows you to see cracks or any negative features on the casting surface. Radiography, everybody likes to take x-rays. The reference x-rays aren't very definitive in terms of being able to be evaluated, but they are the current standard. We actually did a gauge R&R on the RT standards, and you can see that at level 2, 3, and 4, you're at over plus or minus 1.5 for the 95th one-sided confidence interval. And so basically, this is really a subjective standard. We even found that the best, highest reveled NDT guy doing the same material twice, 128 x-rays of a flat plate, so there's no features to screw him up, and he could see the surface, actually only agreed with himself about 40 or 50% of the time. So really that 50% probability of agreement is fairly common. It's common in lung x-rays too, by the way, for tumors and for TSA catching people trying to get guns in. So we actually have proposed a standard where you measure the longest length in the radiographic image, and then you divide that by the width of the casting or the thickness of the casting. If I take the x-ray standards and take the longest indication and divide it by the width of the x-ray film, you can see that for these three categories of indications on the radiographic film, I actually get a fairly nice match with the current standards. You also see that even when I see an indication that's 50% the width of a test bar, I'm still right at the yield strength. And so these radiographic indications have very little effect on the actual strength of the material. And we do radiography all the time. It's the most common thing, especially for first article. Ultrasonic, they do a lot more in Europe. We're not as used to it. We don't do it as frequently, but for critical castings and for complex castings, it's become the preferred way of inspection. And so we have, you basically ring it with a sound, and then you listen for the echo. And if it echoes from the back wall, then there's nothing in between. If it echoes before it hits the back wall, then basically you've got shrinkage or inclusions or something that's causing the sound to bounce off. This is what I was talking about before. Our digital innovative design program, we're actually trying to develop a set of standard NDT requirements. So just like in the boiler code, a common fabrication person can pick out a 3D geometry they want made as a casting, and then we want to embed the NDT and the allowable properties into the AWS D1.1 standard and into the ASTM standards, so that this is seamless to use castings with all the other still mill products that you're used to. Then for high performance equipment, we want to be able to use solidification modeling and identify what the properties are locally, but also identify those areas where I'm concerned about performance and I need some kind of quantitative NDT to assure critical performance reliability. And that means we need to develop some new NDT standards that allow us to do that. We also inspect it for dimensions. We use light sources now. This is an old coordinate measuring machine, but now it's more common to use a ferro arm, or even beyond a ferro arm, some kind of a laser or white light scan. We can meet any tolerances you can meet in any piece of steel that big, but we have to do the same thing you do to those to meet them. You have to machine them or grind them or manufacture them to the gauge. We do have tolerance guidelines. These are in our Handbook Supplement 3. Our traditional tolerances are these tolerance grades, so you may see those on some old drawings. We now point people to ISO 8062, and we give guidance on what levels are appropriate in Handbook Supplement 3. Different processes, different casting sizes, and different volumes of casting production can meet different tolerance standards. So we want to be sure that we pick out the appropriate ones, and 8062 gives some guidance there. The other thing you need to be aware of is when I do a point cloud on the actual part and compare it to the solid model, I will see many dimensions that touch the air that may not be where the solid model is. But if it's not tolerance, they may mean nothing. And so one of our current heartburns, and we have a white paper on our website on this, is that when you compare a solid model to the actual dimensional picture, you need to be sensitive to the fact that if it's touching air and it's not toleranced, then the things that show up as red may be no problem at all. They may be completely consistent with your design intent and with the requirements of the part. Everything you ask us to do, we have to pay somebody to do. So when you over specify quality requirements, you make sure that it takes us longer to make the casting, and it makes it more expensive for us to make the casting. One of our biggest problems right now in quality is many of our large customers have taken the castings that used to be produced in North America and have gotten low-cost producers in other parts of the world. Because those low-cost producers are not using the same common commercial practices we do, commonly there were quality issues that needed to be resolved. Those quality issues from overseas suppliers led to increasingly tightening of the specifications to try and get those low-cost producers to meet the expectations. Then finally it was given up on because of trade or tariffs or whatever, and those castings now are sourced in the US. They're much more expensive now because all of those additional quality requirements that were imposed because of the low-cost suppliers' non-compliance with ordinary commercial expectations in North America now require the North American supplier to do the inspection, and oftentimes those specifications are tighter than the common commercial practices which were acceptable are, and so that meant that the price has been driven up by these additional inspections. So with that, we have 2 free publications, a summary of standard specifications as a handbook supplement, that's free on our website, and also the dimensional tolerances. If you have any questions or you're interested in the DID program or anything, this is my contact information.